Hello and welcome to my channel. Today I will be discussing solving one particle one-dimensional Schrodinger equation by Numerov method using ForTran. To be honest and frank, this discussion is actually an extension of a previous discussion, the same problem, but using Excel, not ForTran. But it was basically Numerov method to solve one-dimensional Schrodinger equation. So, what is the Numerov method? Basically, it's a numerical method for solving second-order ordinary differential equation. And the Schrodinger equation, one-dimensional, is a second-order differential equation. So, we can apply the Numerov method for solving such problems. Particularly, as example, we can solve one-dimensional particle in box problem, simple harmonic oscillator SHO problem, and of course a few more problems. But it's not that any one-dimensional potential can be solved by this method. And as you know that this Numerov method consists of a number of components as part of the method. First of all, it starts with a little bit of maths for chemist. Then you have to have a little bit of quantum mechanics, all the preliminary parts of course, and then it requires numerical analysis, mainly Taylor series, and then algorithm part because we are using a ForTran language. So finally the language and its syntax and its program itself. So it's many in one, and that's why I compared it with, as you have seen in my last video, that if you have separately a dish of rice, dal, and a few more delicious side dishes, that could be a grand collection. But sometimes we need, or we prefer to have this kind of recipe, which is a mixture of so many things, and that mixing itself makes it more tastier, healthier, nutritious, and of course economical. So we call it in Bengali by khichuri. So we have already prepared this recipe khichuri in a last video, which is Excel for Chemists, PCTF series day 9, solving Schrodinger equation by Numerov method using Excel, and that is available in my YouTube channel. The channel name is Priyatosh Dutta, and it's all on learning and teaching with a motto: master your mind and don't allow your mind to master you. So let us quickly go through the preliminary parts, warming up, a little bit of dimensional analysis. So as we have explained earlier, that we need to have a Schrodinger equation dimensionless. That means we have to transform the Schrodinger equation as such to this form. We suppose that this is the variable, reduced variable or dimensionless Schrodinger equation. In short, if you call 2VR minus 2ER as GR, then the Schrodinger equation dimensionless looks like this, where R suffixes R, they stand for reduced variables or dimensionless variables. So for that purpose, what we did, we got 4 reduced variables as they arise in this equation, namely XR, VR, SHR, and ER. How did you do that? Simply by using 2 parameters A and B, new parameters. Of course, they are function of the system parameters. Say for example, in simple harmonic oscillator case, the system parameters were M, H bar, and force constant K. So how did we get all these reduced variables using A and B? By this way. So A and B were designed in such a way that AR is simply E by A, energy by energy. So A of course has the dimension of energy, and hence VR being potential energy, so V by A also gives you the reduced potential energy, and B is such that X by B gives you the reduced XR. So that's how we design A and B, and we got XR, VR, and ER. So out of these 4 reduced variables, we all 3 we have got except psi r. So what about psi r? And I suppose that psi r is like this. Let me define quickly why it's like so. As you know that psi square, or precisely mod psi square, gives the probability density. So psi square dx gives you the probability, and which is dimensionless. So psi square has and must have the dimension of length inverse. So psi is length to the power minus half or b to the power minus half. So I have justified that psi r looks like this. So now we can say that we have got all the 4 reduced variables needed for our dimensionless Schrodinger equation. But the question now arises that what are the forms explicitly A and B, how do they look like in terms of M, K and H bar? So that's an easy exercise just by dimensional analysis. If I express A and B in terms of the fundamental M, L, T, mass, length and time, and similarly if I express M, K and H bar in terms of M, L, T, then we will get 2 sets of equations, all are in terms of M, L, T. Then we can suitably equate to get finally A and B, and they will come like this for SHO system. Of course, if the system varies, then the expressions of A and B would be slightly different. For example, in SHO that we have done in this video, but we have explored a few more which are not being presented here today. But we have done box problem, 1D box problem. You see A and B looking very different from that of SHO problem. We have done this kind of special x to the power 4 formula potential, and also we have done a few more including the ammonia inversion related potential and a very interesting double well potential. But we are presenting here only simple harmonic oscillator today. So let us go back to our main problem that we started with, Schrodinger equation, but now we have got in terms of reduced variables. So this is the second order differential equation. Now we will replace V, psi, E by their corresponding reduced variables, because in the meantime we have got all the reduced variables. So if you do that, in the right hand side you get an expression like this, except the left hand side, that is psi double prime, which is still to be expressed in reduced form. And I suppose that this is the relation between psi double prime and psi double prime r, and one can easily justify that why it is so. So here it is given, and I have explained in the last video that you start from x, r and x, this relation, and you use the derivative, and you just take the double derivative starting from psi, and you can show that this is the final expression for psi double prime. So we have used here in this equation psi r double prime b to the power minus r. So this is, now we can say that we have got the complete Schrodinger equation in the reduced form. So let me write it again to simplify a little more. How? It's very simple. Just A is taking out and rearranging A and B in proper positions, and then on both sides B are there, so cancelling out, finally we get an equation like this. Okay, so if we club together AB square finally and bar into M by H bar square into this is called GR into psi r. So this is equation 1. We can say at this point this is the reduced variable or dimensionless Schrodinger equation. Now special focus on this portion. You see all the variables are dimensionless, so naturally this taken together must be dimensionless. That means the dimension of the first part must be the inverse of the second part in dimension. So AB square should be H bar square by M, and that we can check easily by explicitly writing A and B in terms of M, H bar and K, and we can show that AB square would be H bar square by M, as it is intuitively declared. So what happens? We get AB square is h bar square by m. So if we just put it here, and you see they will cancel out. So equation 1 is reduced to be even more simpler. It looks now like psi r double prime equal to 2vr minus 2er into psi r. So that is the simplified form. And if I call this to be gr, 2vr minus 2er is gr, then the simplest form looks like psi r double prime is gr psi r. So this is the second order differential equation that actually we have to solve, right? That means we have to get the psi r and as well as the E in G. Okay, so how do we do that? Of course, one can go for an analytical solution, analytical method, and by that way he or she is supposed to get psi as a function of x as a continuous function. But we are using a numerical method, Numerov method, so we will be not getting psi as such as a function of x, continuous function. Rather, we will be representing our psi like this. That means we will be choosing a grid point on x, x0 to xn with a suitable interval, equal interval s. So x0, x1, x2 dot 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 x max or xn, and our function would be represented on that grid. That means I will be getting the values of the function at different x, and for simplicity we will represent fn minus 1. That means xn is the given point minus interval s, that would be the n minus 1th point. So if n minus 1 is actually the value of the function psi at the n minus 1th point, and so on. Fn like at the point xn, and fn plus 1 is at the point xn plus s. So this is how we will represent our wave function of the grid. And now we need it requires a little bit of numerical analysis, which is simply Taylor series. What does it do? Taylor series, it expands a function around some given value. Say fx is a function and we want to expand f as around x by interval of h. So if x plus h looks like this, as you know. Similarly, x minus h also I can expand. And if f is really, in my case, it is the wave function. So in other words, we can write psi xn, that is the nth point, then plus minus s on both sides of the point xn. I am expanding psi n. So the expansion looks like equation 4 and 5, giving for psi x plus s and psi x minus s. So we just don't bother much right now about the lengthy right hand sides. But one thing is interesting to note, that this first, third, fifth, that is the odd power of s, these terms are exactly same but with opposite sign, plus minus, plus minus. So if I add equation 4 and 5, the odd power terms will cancel out and only the even power would be there. So we will get psi x plus s plus psi x minus s, that psi, 2 psi, and so on. The second and the fourth they will get. So equation 6 is so good so far, but with slight problem in evaluating this fourth power, psi fourth power x. So s to the power 4 psi 4x, it may give a little bit of complicated things. So let us try to simplify it a little more. How? Here is a mathematical trick. What we will do, we will try to eliminate, or rather to express this s to the power psi power 4 in terms of psi double prime only. How we can do that? The recipe is, you double differentiate both sides of 6 and multiply by s square. So one can easily check that if you do that, then you will get this expression. I am repeating on the next page. So you will get this expression. Now what the solution is, because s power psi fourth power and even psi fourth power are here, but here s to the power 6 is involved. So x to the power 6, as you know, is very small because s itself is very small. So we can neglect this portion and then we can express s to the power 4 psi 4 in terms of psi double prime. So that is exactly what we wanted to eliminate the problem regarding psi power 4 term, and now we simply put it in the next. So after removing this approximation, that s to the power 6 term, we get this s4 psi 4 in terms of, you see, double prime only double primes. So now we can put this 7 in our original equation, the 6, and what we will get, we get this. You notice that only psi and psi double prime are there, not psi triple prime or psi fourth prime are there, not there. Okay. And if you remember that original equation, I mean reduced variable equation is this, then you can put double prime wherever you see psi double prime, you can put the gr psi r. So after putting that, you get this final form. Again, don't bother about the right hand side right now, that you can easily manipulate on your own. Just see how it's going on. So finally, in the box, I get on my left psi x pluses, and on my right psi x minuses and psi x. And of course, psi x plus is also here on the right hand side, but okay, let us see what we can do on that psi x pluses on both sides. So I'm writing it again on this page, and in our computational term, if I replace psi x as psi n, that's nth point psi x is psi n, and so on, then the same equation looks like this. So you see, on your left and right, both sides, psi n plus 1 is here and psi n plus 1 is here. So we have to manipulate a little bit more, so that psi n plus 1 can be brought in one side only, that is the left side. So if we do that, finally you will get an equation like this. Now you can easily check that on the right hand side, psi n is there, psi n minus 1 is there, and psi n minus 1 is there, but no psi n plus 1 or higher term are there. That means we can say that we have got psi n plus 1 in terms of psi n and psi n minus 1. That means psi at a given point I get if the previous consecutive two psi values are available. So for psi 1 and 0, if they are available, then I can evaluate psi 2 and so on. So the point is like this, that if psi 0 and psi 1 are provided, then you can get psi 2. Then using psi 1 and psi 2, you can get psi 3 and so on. Finally, you get the nth max point or psi at the x max point. Of course, g in this expression psi n plus 1, you see g is there and g is a function like this. That means g contains e. That means psi n, of course, is a function of energy E. So psi n is a function of E. Okay, and we demand that this psi n, that the extreme right hand x point, psi at x max, that must be equal to 0. Why so? Simple quantum logic, that well-behaved function must vanish at both the infinity, plus and minus infinity, and that logic itself gives you another clue that the psi 0 point, why you will assume that psi 0 must be 0. And psi 1, of course, something to say. Psi 1, you can safely assume a very small number, either positive or negative, because whatever the psi state or level is, if psi 0 is 0, then psi 1 is definitely not going to jump up anywhere far. So it is enough to say that psi 1 is very small number. In fact, even if you take a little bit higher number, doesn't matter, because that amounts to say that you can change as by normalization procedure. Every point would be multiplied by some certain factor. So it doesn't really matter whether you are accepting psi 1 as a very small or little small number. So now the question is, your target is to get E and psi n, right, or the whole set of psi. So psi n as a function of E and equal to 0. That means you can either directly solve this equation psi n equal to 0, for E, and once you get E, you can put it back to get the psi also every point. But that's a direct method, but here we are not using the direct method. Rather, what Numerov did, a beautiful iterative method for searching the secret E. So E is something secret value, and we are searching E by some beautiful iterative method. So now you are ready for computation. Okay. So let us first have the logical structure of the program, what we call the algorithm. What are the steps? The program must have a set of inputs, right? So let us jot down what are the inputs. Of course, we need the minimum leftmost point x0 and the rightmost point xn. That means you are choosing the grid, and you have to fix that how many numbers of points that you have to frame the psi at different points. So n is the number of grid points, and then you need the initial psi 0, as I have logically explained that it has to be 0 and psi 1 has to be a small number like 001 or 0.0001. And it has to be small, but really I have explained choice doesn't matter. And then n level, that means number of energy level that you are interested in. You may be interested to find only the ground level, but maybe more than one level you are interested in. So in ForTran you can have as many as you like. So n level is the number of levels that you want, and n trial is the number of cycles for each en. That means for a given nth level, you have to search. It's a iterative search method. So how many cycles it will complete? I will put a number from outside that it is n trial, and then EH and EL, the upper and lower bound of some input energy. Why these two are needed, I will explain later. Then after getting x0 and xn, we can evaluate the interval s. So xn minus x0 by n minus 1. So the input and the evaluation of s is good enough. Now the main computation part. So in terms of ForTran language, I will say start a loop or do loop. But here in algorithm, I am just saying continue ek steps where k is 1 to n level. So it is a loop over energy level, and that level goes from 1 to the number of level you have put, level n level, say 5 or 4 or 3 or even 1. So it's a loop on energy level, and inside that loop first it reads a guess value of energy. Guess value, it can be a wild guess as well actually. And then the second part, actually the second go do continue portion, or again a repetition job, and this time the do loop or continuation is over the steps trial 1 to n trial. So that means for a given energy level it will search how many times? N trial number of times. Now inside this loop it will search, as I have told you, but how it will search? For that you need another loop. I have given 3 different colors for the 3 different continue or loop statement. So the purple color continue or do is over the psi I step, because you have to now evaluate the psi value at different x values. So psi 0 and psi 1 are given, so you start from 2 to nth point. Okay, so after getting psi, you can evaluate a g. V is known for the system, it's a function of x only, and E that you have chosen in this stage, value of energy you have guessed. So this is particularly for SHO problem, you have used Bx half kx square, and then using the formula, as I have mentioned already, you are translating this formula to find psi ni plus 1 from the earlier 2 points, that is psi I and psi I minus 1. So you have now got the full set of psi at different points, all the points, and then what we will do? We will modify E until psi n is 0. So you have started with a trial or guess E Of course, if it is not an exact energy, then you will not get the perfect set of psi, in the sense that your psi x max, that is psi nth point, and that would not be 0. So you will not get a normalizable wave function unless E becomes exact energy. So you have started with an arbitrary guess. So naturally you have to modify E until you get psi n equals to be 0. And then once you get it, then you report that energy value as the kth energy value, because it is over k equal to 1, 2, 3 dot n level. So that is how it works. But two questions arise. First of all, read a guess value of energy. Now, is there any clue how to guess this E value? It's a difficult question. And more importantly, the second interrogative sign, that is modify E until psi n is 0. So how do you modify, right? So that is the two questions we are leaving at this point. And for the purpose of how we can solve it, we will actually be playing a game. The name of the game is searching or reaching by bracketing. Searching or reaching by bracketing. Well, the game is that you are searching a secret value, E secret, and you have been given two lower and upper bound, E lower and E upper, but you know where the secret value is. That's why I am saying reaching or searching. In present case, it is just reaching. That means you have to develop an algorithm starting or using this upper and lower bound in such a way that you can exactly reach this secret E value, what you know actually. So what we can do, we can follow such a logic. We have to take first the lower bound and upper bound, say EL for lower and EH for E higher, and here somewhere suppose that the secret value is there. So what I will do, my initial guess would be simply to take the average of EL and EH, and that I don't know what that average value where would be. It may be either on the right hand side of the ESEC or on the left hand side of the ESEC. That means in the 0 region or in the region 1. So I take the average. Now what happens? Suppose it is somewhere here. It is somewhere here. That means EG is less than ESC. So if it happens to be here, then in my next step I will readjust EL or reassign EL to be the average value EG. So EL gets EG. If it is here, that means I am shifting my lower bound towards right. That means I am decreasing the range of my lower and upper bound. On the other hand, if it happens that the EG, that is the average, it is greater than EASCC, that means somewhere here, that means in the region of 1, then what I will do, again I want to reduce the range, but this time I will make this EH to shift towards left. So the distance is decreasing, that means now EH is redefined as EG, right? So again after redefining either EL or EH depending on which side the EG comes initially. So after the first cycle, I again take the average, right, EL plus EH by 2, because this time either EL or EH has been changed, and I will get a new EG, and that new EG may be either on the left or on right. So again I will follow the same logic. If it is on the left, then EL would be redefined to that value, or if it is on the right, then EH will be redefined to that value. But in any way, I am going on decreasing the range, or in other words I can say that I am making EL and EH to converge or merge to each other. They are gradually switching over to a point, and that point must be EACC, though I know to start with where that value or what that value is. So this is the I can say it's a simple game, and we can run a program for this purpose only, and the result is already shown that I have taken the ESEC, say that secret E value is supposed to be 1, and I have just given n trial only 20, then it goes on like this. So EG initially 10, I have taken EL as 0 and EH as 10. So the average is 5, and which is on the right side of the exact value 1, or E sec value 1. So since it is the right hand side, so that means EH is reassigned to be 5 and EL remains the same. Then you take the average again, 5 and 0, that means 2.5. So again it is on the right hand side of 1. So EH is taking the value of 2.50, but EL remains the same. And then again you take the average, you get 1.25. Again it's on the right hand side. So again EH takes the value of 1.25 and EL remains the same. And then again you take the average. Now you get 0.63, which is on the left hand side of the secret value. So since it is left hand side, then EH remains the same, 1.25, but the lower bound now takes up the new value 0.63. So now you have to take the average of 1.25 and 0.63, you will get 0.94, which is on the again on the left hand side. So again the EH remains the same, but EL takes the value 0.94, and now if you take the average 1.09, now it goes to the right hand side, that is region of 1, right? And it goes on like this, and you see one thing, that gradually EL and EH, they are approaching towards each other, and finally they are same, exactly 1.1, 1.1. So there is no point to give the cycles any more run, because already you have got the converged value, and it finally gives the E-sec or secret E value is 0.9999, that means 1, and that I gave the number 1. So it's an interesting, beautiful game. Okay, for your curiosity, I can run the program quickly. You just follow. This is the program, and I am just running it quickly, giving some secret E value as I have shown with 1. So let me show here with say 0.5 or 1.25, whatever it is, and giving two upper bounds and lower bounds. Lower bound is 0 as usual, and upper bound I have given 10. So E-sec, say I am giving this time is 0.5, and n trial again say give only 20. So let us see whether it is giving you, yeah, it is. You see the final result, secret E is 0.500000 something. So and EL and EH gradually converge to the same value as that of the exact or secret E value. So that's fine, that the program is running. Now the question is that how we can use this for our purpose. Okay, so let us see. This is the program that I have run, and now the question, important question, that in earlier game program we supposed that we know the secret E value, and we could apply our logic comparing the EG or guess energy compared to the secret E value. But in our case, we don't have the secret E value. Rather, we are searching for the E secret value. So the same logic, can it be applied? A problem, a question. Of course, we cannot apply on the basis of comparison with energy, because energy itself is not known and we are in search of that energy. But then the question, is there any other source that basically we can be applying that same logic, left side, right side, and reassigning the lower and upper bound, but not on the basis of energy maybe, but something else, and what that something else can be? That is the question. Here gives the answer, nodes of the wave function. And as you know, for SHO system, the ground state has no node, the first state has one node, and so on. The kth state has k number of nodes. So it looks like this. So the ground state, 0 node, 1 node, second, third, fourth, and so on. So this is the number of nodes in a Numerov method solution as a function of the energy E guess. So we can use probably the same logic as we have applied in the game problem, that instead of energy comparison, now we can compare the node number. So the search is not based on energy this time, but on the number of nodes. How? The same thing, the same averaging, but this time if nodes equal to k, then you reassign EL to E, that means you are moving the lower bound to the right side. Or if the nodes is greater than k plus 1, then you reassign the EH, that means you are shifting the upper bound towards left. K, if you say k is 0, that means you are interested in the ground state, then 0 and 1, that means 0 and 1, no node and 1 node, that means you are moving around this E1, but you don't know where E1 exactly is. But if you apply the same bracketing procedure, then of course the upper and lower bound will converge to a single value, and which is of course the perfect energy secret value or E1 exact value, because then only we can get the psi max to be 0. So that is the beauty of this Numerov method. It is using completely a different approach by bracketing technique. So now we are really ready for the final program. So final program, the basic job is to translate this psi n plus 1 as a function of psi n and psi n minus 1, where s is the interval, g is, as you know, in terms of v and e only you can express if you know the x only, and then psi n and psi n minus 1 are known. So you should be able to evaluate the left hand side psi n plus 1. Exactly that we are translating in this program. Okay, this part it gives you the input x0, xn, interval evaluation, then lower bound, n trial, how many levels you want, etc., etc. And then there starts, as I mentioned, that there are 3 continue. So that means in computer language there are 3 do loops. So one loop and all are expressed in different colors. So do 5, it is over the j, that is level 1 to L level, that is how many levels you are asking for. And then another blue color do loop starts, which is on trial, how many trials or cycles you will accommodate for a single level. And in this trial, actually what it will be doing, in another loop it will evaluate the psi n plus 1. Okay, that is the maximum point, x max, and by that calculation you will calculate the node also. And here that important game logic is there, that as I mentioned, that nodes greater than k plus 1, then EH is E. So if node nn is the number of nodes, greater than j minus 1, j is initially 1, so 1 minus 1 is 0. So if the number of nodes is greater than 0, then the higher bound is reassigned to the average value or E or EG. Or else if the number of nodes is k, then else the lower bound would be reassigned to EL minus E and E. So here exactly that logic is supplied, and then 10 continue the loop, one of the loops, and the external loop 5 continue ends here, and then pause stop end. So that is the main logic, and now I think it's time to run the program to finally get the eigenvalue, etc. So let us get ready for. So here is the program. So I have used some array x for the points, grid points. P array stands for the wave function psi. P stands for psi, and G as we have defined 2VR minus 2VR. And all the inputs are given directly. N is slightly higher, 1000. It's not needed that much. And the lower bound and upper bound of x, that is minimum x and maximum x, are also given, minus 10 plus 10. This is the interval, and then the lower bound is 0. I have given n trial to be 500. It's not needed to give that much, that big a number. And I am here interested in 5 levels: ground, first, second, third, and fourth. And then the first 2 wave functions are given as 0 and a small number, and these 2 are nothing but in my array x1 and x2, and then it will start the first loop over level, and okay, if you go ahead, then you will see that after the first loop, EH is 10, the upper bound of energy, and then the loop over the n trial it goes and it takes the average, and it starts counting number of nodes to be 0 initially, and then it will check and finally give you how many nodes are there in the function. And the g at different x values 1 and 2, g is its calculate. It requires only the x and e is already supplied as the average of this higher and lower bound, and then another loop starts from for psi loop. We call it psi loop because it's 0 1, so 2 to n minus 1, so it evaluates all the psi. That means psi at all the points, and also gives the number of nodes available. And then finally that game logic is also here by this portion, that n greater than j minus 1, then eh is e, else el is e. So the upper and lower bound are redefined according to the problem, and then finally write. So let me run the program for SHO system. Where I have assumed that mass is 1 unit, atomic unit, where K is also atomic unit. So I have run the program. Now it's see, you see that level 0, 1, 2, 3, 4. So 5 levels it has produced, and energy. The ground state is 0.499999. I think you will agree with me that I can safely accept it as 0.5. The second one is 1.5, the third one is 2.5, 3.5, 4.5. They are coming in this fashion because I have deliberately taken H bar an atomic unit, that is 1, K also have taken the value 1, and M has also been 1. So the exact value, so H nu is 1, so the exact energy expression is n plus half H nu. If H nu is 1, then E ground, that is E0, would be simply half, that is 0.5, and E1, that is the first excited state, that would be 1 plus half, that means 3 by 2, that means 1.5, so 1.5. And on the right hand side it shows you the error means the computed value, difference between the computed value and the exact value, because we know the exact value of SHO, and that comes as you can say they are almost 0. So I think it has produced excellently the energies. Okay, if you are interested in the wave functions also, then you can store it separately in separate file, the p files, this p array, and you can get the wave functions as well. And if you can have a good grapher package, you can even plot those p values, p array values against the x array values. That means the psi x as a function of x, and you can have beautiful wave functions plot, including the number of nodes it will show. So that's all about the programming part, and I think that's all about our today's discussion. So thank you very much for listening. It's really an extension of the earlier video, as I mentioned. Earlier I have done it using basically Excel, which gave you the plots, and today I have done with the ForTran. The main advantage of ForTran, of course, it gives you more than one level, energy level, exact energy values by a single run, which is not possible in Excel. On the other hand, in Excel you can directly and easily get the plots, which is not that easy in ForTran. So thank you again for watching, and I will be happy if you please come back with your suggestion, comments for whatever you like. Thank you very much.